Welcome to the Scientific Dose. I'm taking on the role of your medical tutor today, and we are going to embark on a seriously rigorous journey. We're going all the way from identifying fatally flawed data to delivering flawless patient care. We've got a ton of high-yield concepts to master today, so grab your notebooks and let's get right into it. Here is our incredibly high-yield syllabus for the session. We're covering 1. Foundations of research accuracy, 2. Selection bias and clinical impact, 3. Information bias and misclassification, 4. Confounding factors and evaluation, 5. Validity versus reliability, and wrapping up with 6. Evaluating studies for patients. All right, Section 1, Foundations of Research Accuracy. Let's build that groundwork. Take a really close look at this silhouette of a human head. Right inside it, you'll see a classic balance scale. On the right side, the word fact is stacked up super heavily, but look at the left side, stacked just as heavily, pulling it right back down is the word bias. I want you to burn this specific image into your brain because bias isn't just some random little mistake. No, it's a systematic error baked right into the design, conduct, or analysis of our research. It literally acts like a heavy weight on that scale, constantly and predictably pulling our measurements away from the true factual value we're trying to find. Okay, let me drop a high-yield exam tip for you right here. You absolutely have to know the critical difference between random error and systematic error. Random error, that's just unpredictable variation happening by pure chance. Think of a patient's blood pressure. It naturally fluctuates slightly up and down every single time you take it. It doesn't consistently bias the results in just one single direction. And the great thing is, you can shrink its impact just by increasing your sample size. But systematic error, or bias, that is a consistent structural deviation. Imagine you have a faulty clinical scale in your office that always adds exactly plus 2 kilograms to every single patient's weight. No matter how many thousands of patients you put on that scale, you cannot fix that error just by increasing your sample size. It's a fundamental flaw in the tool itself. Moving right along to Section 2, Selection Bias and Clinical Impact. It's kind of wild, but simply choosing our patients can completely alter our study outcomes. Look intensely at how this visual flows. Over on the left, we've got this massive gray circle representing our target population. It's super diverse, filled with colorful little figures representing all the different types of people in the real world. But follow that red arrow pointing to the much smaller, isolated green circle on the right. That is our actual study sample. Selection bias rears its head when the probability of a person being pulled from that big, diverse pool into our tiny green sample circle differs based on what they've been exposed to. When that happens, boom, our tiny green circle suddenly no longer represents the reality of the larger population at all. Let's put this into a real-world clinical scenario so it clicks. Imagine you want to study general hypertension in your city, but to make things easy, you decide to pull your study sample entirely from patients at a highly specialized tertiary cardiology clinic. That right there is called clinic-based or referral bias. Those specialized patients are naturally way sicker than the average person, so they're completely unrepresentative of the guy walking down the street. Another classic exam favorite is Bergson's bias. This happens when researchers get lazy and just use hospitalized patients as their control group. Since hospitalized controls often overrepresent severe exposures that are totally unrelated to the primary disease you're actually trying to study, you instantly create a totally false association. You've essentially ruined your study's representativeness before collecting a single piece of data. We also need to contrast how different study designs practically invite completely different biases. For instance, case control studies are highly prone to something called Neyman bias, which you'll also hear called incidence prevalence or survival bias. Here's what that looks like in the real world. If you are studying a rapidly fatal disease, the most severe cases might tragically pass away before they can even be enrolled in your study's inclusion window. By only studying the survivors who made it in, your case control study entirely misses the most intense exposures. Now contrast that with cohort studies or surveys and interviews. Those are highly prone to response bias and interviewer bias. If an interviewer unconsciously asks a leading question, or if only the healthiest, most enthusiastic people bother volunteering to answer a mailed survey, your resulting data gets completely skewed away from reality. Fortunately, we aren't helpless here. Researchers have specific prevention strategies to fight this. Let's walk through a great step-by-step example of mitigating volunteer and response bias to make sure our study population actually reflects the real world. Step 1, you have to clearly identify your exact target demographic from day 1. Step 2, randomize your outreach. Don't just stick flyers on the bulletin board at the local gym, because then you only capture healthy volunteers. Use random phone dialers or generalized community mailers instead. Step 3, offer structured incentives, so participation isn't limited only to highly motivated people with lots of free time.
And finally, step 4, strictly compare your final participant demographics against known census data of the general population to guarantee you have actual demographic alignment.
All right, Section 3, Information Bias and Misclassification. When our actual data collection process is fundamentally flawed, our outcomes completely suffer. We have two key visuals here to illustrate this. On the left, there's a stick figure violently scratching their head with a giant red question mark, clearly struggling to remember something. And on the right, we see our familiar bias scale again. This brilliantly captures recall bias. Let's use the classic flossing versus cavities real-world example. If you ask people with a mouth completely full of painful cavities, those are our cases, about their past flossing habits, they are highly motivated to think deeply and scrutinize every single time they ever forgot to floss. But your healthy controls with 0 cavities, they just brush off the question and casually assume they floss normally. The error in remembering naturally differs between the two groups, which wildly skews the study's results. And this graphic brilliantly shows exactly how this misclassification mathematically harms us. Look at the top, in the green box. That's non-differential misclassification. Notice how the grayscale is perfectly balanced? If the measurement errors are roughly the same in both Group A and Group B, it naturally weakens the association. It biases the result toward the null, or essentially 0 difference. But look down at the bottom purple box. Differential misclassification. The scale is completely tipped sideways. The errors are vastly worse in one group than the other. This is a non-random error, and honestly, it is absolutely the most dangerous form of misclassification because it can wildly overestimate or entirely underestimate the true medical association. So to fight this, researchers rely on strict prevention strategies to minimize both interviewer and information errors. I want you to memorize every single one of these 4 specific bullets. First, blinding. If the researcher physically doesn't know who is a case and who is a control, they literally cannot unintentionally ask leading questions. Second, strict data protocols. Every single patient must be evaluated in the exact same rigorous manner. Third, standardized questionnaires. Everyone gets the identical phrasing, leaving absolutely 0 room for subjective, on-the-fly interpretation. And fourth, verifying with written records. Never, ever just rely on flawed human memory. Pull the actual physical medical charts to relentlessly confirm those past exposures. Section 4, Confounding Factors and Evaluation. Let's see how things get tangled up. External variables can completely hijack our clinical data if we aren't paying attention. Focus intently on the top right green quadrant of this visual. We see the classic confounding triangle. Now look at the bottom arrow. It implies a direct relationship between smoking and lung health. Pretty straightforward, right? But look at the green eye count of the people sitting at the very top point of the triangle. This represents a third outside confounding factor. For a real-world example, imagine that factor is working in a toxic coal mine. This third factor is biologically associated with both the exposure and the outcome, which completely tangles up the relationship and creates a dangerously false association if we aren't careful to account for it. Confounding specifically threatens the accuracy of our study results by masking the true biological reality with a completely distracting third variable. Next up, Section 5, Validity versus Reliability. Okay, this is an absolutely critical foundation for your exam prep, so let's define these concepts using incredibly clear and simple language. Validity simply means accuracy. Are you actually hitting the true value or the dead center of your target? If your study is valid, it measures exactly what it claims to measure. No more, no less. Reliability, on the other hand, just means consistency. Are you hitting the exact same spot repeatedly every single time you measure it? Now, here's the catch. A clinical tool can be incredibly reliable, like yielding the exact same wrong result 20 times in a row. But if it's consistently wrong, it has absolutely 0 validity. To really lock this into your memory for the exams, let's look at the bottom 2 quadrants of this fantastic diagram. Look closely down at the bottom left purple box. You see a checklist on a clipboard with a bold check mark right at the bottom. That perfectly visualizes validity. Did we hit the true mark and check the right box for our population? Yes. Now shift your eyes over to the bottom right yellow box, representing reliability. Look at those 3 repeating bullseyes lined up perfectly in a row. They look exactly the same time after time after time. That visual of perfectly repeating targets is the very definition of reliability. And finally, Section 6, Evaluating Studies for Patients. Let's bring it all home. To apply all of this rigorously, I've created a clinical checklist for evaluating literally any research study you ever encounter. Please do not skip any of these details when you're reading a medical paper. Number 1, the selection bias check. Ask yourself, how were these subjects actually found? Did the researchers lazily pull from a specialized tertiary clinic? Did severe cases die out early? Does the sample truly look like the general population? Number 2, the information and measurement bias check. Were the scientific tools strictly calibrated? Were the interviewers appropriately blinded? Did cases recall their histories way differently than controls? And number 3, the confounding factor check. Did the researchers scientifically adjust for age, smoking, or other hidden third variables that could create that dangerous false association triangle we talked about?
And this brilliant checklist illustrates exactly why all of this matters so deeply in the real world. Bad data leads straight to bad clinical guidelines, and bad clinical guidelines ultimately harm our real-world patients. As future medical professionals, you have a profound ethical responsibility to thoroughly evaluate the evidence presented to you. You aren't just memorizing random errors and bias skills simply to pass a test. You are learning how to defend your vulnerable patients from flawed science. So I leave you with this final provocative question. The next time you read a groundbreaking new study recommending a powerful new drug, will you just blindly accept the author's conclusions, or will you fiercely examine their data for systematic bias and tipping scales to ensure flawless patient care? Keep questioning, keep learning, and I'll see you in the next session.